I would like to describe a field in which little has been done, but in which an enormous amount can be done. This field is not quite the same as the others in that it will tell us little of fundamental physics, but it will tell us much about the strange phenomena that occur just below our perception. In contrast to the natural philosophers of the past, the scientists of this field delve into the recesses of nature and show how she works in her hiding places. Their quest is to understand and create the imperceptible. After all, there is plenty of room at the bottom.
Hey everybody, welcome to the Materialism podcast, an exploration of the past, present, and future of material science and engineering. My name is Andrew Falkowski, and I'm joined by Jared. Jared, how's it going?
It's going good. Summer semester's over now, and I reveled in my 2 weeks off before getting right back into it.
How's the new semester going?
I don't actually really know yet because one of the professors is taking the first week off because he's having issues getting the classes recorded. And since I'm remote, I can't see anything if they can't get recorded. He's very nice and he's like working with us on this. So I don't blame him at all. But I guess he's having some technological issues. So we're not really sure what the class is going to be like just yet.
That's a bummer. Hopefully he can resolve that quickly. I'm not sure. He's probably running out of time.
No, he got it. He did get it sorted.
Oh, okay.
By now, I think. But I have yet to watch the first class just yet. But I'm excited. It's a space structures class. I've always kind of wanted to do a space structures one. I'm very interested in that aspect of it because I think it's obviously a little different than making structures on Earth. So yeah. I'm excited for that. What about you? What have you been up to?
Well, semester started here too. Been dealing with the usual start of the semester things. A lot of weird grad school things.
You're all done with classes though now, right?
I am. I just have to take the seminar. Yeah, and then besides that, I've been using baking as a creative outlet. I'm into making biscotti.
I remember we got dinner recently and you were talking that you had made a biscotti and it was good, but you said it wasn't there yet.
That is an unspeakable batch. That was batch one. It was terrible. I completely screwed it up, and
okay, I was trying
frankly,
to be nice.
It's not my fault.
I was trying to be nice, but yeah, you did say you did bad.
The recipe left out a crucial step, and that just caused it was a disaster. I have gotten a lot better since, and I've really been able to apply some material science knowledge to it, too.
Well, what is cooking if not material science? We had that episode about chocolate as material science, if you think about it.
Yeah, that was a long time ago.
Oh, also speaking of creative outlets, I've been on the 3D printing grind, which has been a lot of fun.
You got a resin printer, is that right?
I did get a resin printer, and it's messy. It's really, really disgustingly messy.
You have to pull it out of the goo, and you got to wash it, and you got to put it in that LED curing oven thing.
The worst part is I had the tank explode, basically. There's a hole that ripped in the bottom, and it spilled out, and it sort of seals itself back up, obviously, because the light was still flashing. It was still going. So it was like hardening, but enough spilled out. It spilled all in it. So I actually had to take the resin printer completely apart, like every part out, and do a deep clean. Is that fun
as a mechanical engineer?
Yeah, it was fun. I actually really enjoyed it. The thing was, is if I was doing it for fun to learn about it, it would have been awesome. Doing it because it was essentially completely bricked was not as fun. And then I ended up having to replace a part or two because they were just so disgusting that no amount of cleaning was getting the resin residue off of it. And then my LCD screen, the resin had cooked so thoroughly that when I tried to get it off, check this out, this is crazy. The polarization filter for the LCD screen came off with the resin. And so my screen was fundamentally useless. And so I had to get a new screen. It was an expensive lesson in keeping things clean. And also, I don't even know what caused the resin or this puncture in my resin tank.
That's unfortunate. It sounds like it's up and running again. We had one of those, or a couple of them when I was in industry, and they were awesome. The resolution that you can get, and the quality is just much better compared to an extruder printer. You can make some pretty nice prototype parts.
It's night and day. When it was working, and now that's working again, it was just so incredibly fun. It was just that small down period where, admittedly, probably my fault. I'm sure I did something wrong, but whatever it is, I fixed everything. I got all sorted out where I was like, this is miserable. But it's really fun, and what I ended up having to do to make sure to keep it safe is I got a good glass screen protector for my LCD that was nice hard glass.
What a great transition, Jared. That's what we're talking about today.
Oh, really?
Indeed. Glass is a ubiquitous material. It's all over. In fact, there's several glass items in the room with us right now. But making all this isn't cheap. Glass is made of silica, which has a pretty high melting point, and that that has a pretty big impact, right? In order to heat glass up to the point where it can melt and be processed and formed into all these different form factors that we have all around us, it takes quite a bit of energy. Not to mention that a lot of the precursors to making common glasses like soda-lime glass or borosilicate glass are bonded to carbon, and in the process of making that glass, undergo a calcining process where that carbon's burned off and forms CO2. The U.S. Environmental Protection Agency estimates that flat glass, which is the common glass that's being used for windows and such, has a direct carbon footprint of about 0.5 tons of CO2 per ton of glass manufactured. But a full life cycle analysis found that window glass used in a residential building has the equivalent global warming contribution of about 2.2 kilograms of CO2 per kilogram produced.
Yeah, actually, it's funny. I kind of saw an article that was talking about how, when people think about building, you think about how much CO2 is produced in steel or concrete or things like that. But glass is something that kind of flies under the radar for a lot of people when it comes to its actual impact on our environment.
Yeah, and the split is a little interesting. So about 60 to 80% of that carbon footprint is just from the energy needed to melt it alone, while the remaining 20 to 40% is emitted from the decomposition of those precursor materials.
Dang. So there's clearly some room for improvement here.
Yeah, and so this is where LionGlass steps in. This is from John Morrow's group at Penn State University, and they wanted to address this problem by trying to lower that melting point and make a glass that was potentially commercially viable, while also cutting emissions through both a reduction in energy and a reduction in the amount of carbonaceous products that have to be used. And recently, in July or so, an article came out giving us a little more details about what LionGlass is made of and what its properties are. And so we wanted to dive in that. And in the course of that, we discovered some really interesting glass chemistry. And so in this episode, we're going to be walking through some unique aspects of glass chemistry and what makes LionGlass so special.
I will say that the first thing that caught me about LionGlass was that it was called LionGlass. I thought maybe it was a joke on Gorilla Glass at first. I didn't realize that it's the Penn States or the Lions.
Nittany Lion.
Yeah.
Kind of an embarrassing confession. I don't know what it is about Penn State's logo, but it looks like a shark to me. I don't know if I'm messed up or something. When I look at it, like in a 1 second glance, I don't see the lion.
I don't think that I see that staring at this logo, but I could understand how it could maybe look like the water swirling around and a shark fin is coming out. It's not. I think I do see that. I think that their logo is maybe abstract enough for that.
Well, it kind of looks like they're updating it. They have one that the
I
line
see that,
is much clearer.
I do see. I was on the sustainability page, obviously doing research for this, and I have it open and I can see. Yeah.
Yeah. Okay. So that's that one.
I know. That's one I have. That's when I said.
It's just a little too abstract. I can see it actually now that I'm really taking it in. I can see it a lot better. But
if you look at it looks like a shark circling in the water.
Oh, that's not even how I see it.
Oh, interesting. Okay. Well, clearly, you need to look this logo up and give us your thoughts on it.
Now, this isn't the first time we've talked about glass on this podcast. You can go back to episode 107, where we sat down with some people from SHOT to talk about the interesting glass work that they're doing, and even further, because glass extends beyond just oxides to metals. Episode 99, we had one on bulk metallic glasses for how you can get metals to behave in glassy ways. But we want to take some time to review some of the basics of glass and expand what we'd covered in these previous episodes. As you may know, if you cool a material fast enough, you can prevent the crystalline ordering of the atoms in the solid, effectively freezing them in an amorphous state, similar to a liquid structure. Turns out the rate at which you cool them also affects the degree to which they can locally order, and that can change things like the density and the refractive index. If you looked at glass on an atomic scale, you're looking at basically a random network of oxygens that are going to be bonded to different ions, basically chains.
Mm-hmm.
Glass compositions are often viewed in terms of network formers, ions that are going to form that network,
Sure.
and then network modifiers. These are ions that are going to disrupt that network and change its properties. But it's often a little more complicated than that. A traditional classification system actually has 3 categories that are based on an ion's field strength divided by its ionic radius. Network formers have a very high field strength. These are going to be things like the ions of silicon, boron, phosphorus, and arsenic bonded to oxygen.
Mm-hmm.
Now, the network formers are just one small part of this. In some cases, maybe to enhance the processing, to maybe lower the melting point, or to change its optical properties, we want to change this network. And this is where network modifiers come in. They have a really low field strength, and they're things like sodium, potassium, calcium, and barium. Network modifiers disrupt this network through the creation of non-bonding oxygens. So when Na2O is added, the O2- will break that O-SiO linkage, creating these non-bonding oxygen sites that have like a 1- charge, and then they're balanced by a sodium, for example. The more that you add, the shorter these continuous chains get, allowing them to slide past one another, and that's how you could reduce the melting temperature.
So could you theoretically make a glass using only network formers?
Yes, but you might not want to do that because it'll hurt your processability. Silicon oxide has a melting temperature of 2,000 degrees Celsius. That's really hot, and it would take a lot to actually get up there.
Sure.
Adding things like sodium or calcium, which are often added to, soda-lime glass, for example, a common composition is a silicate with sodium oxide and calcium oxide, lowers that melting temperature down to something like 1,500 Celsius. Still pretty hot, but certainly a lot better. So that's kind of the motivation for why you would add those. The last category are intermediates. These are the chameleons of the glass chemistry world because they can both be a network former and a network modifier depending on the composition of the glass and their local environment. Take aluminum, for example. It wants to typically take on a 3+ charge. So it can be a network former if it's tetrahedrally coordinated, and it can be a network modifier if it's octahedrally coordinated. And this comes down to the glass composition. So if there's sufficient charge balance to allow for AlO4- to be present, then this will act as a network former. Otherwise, it's going to create non-bridging oxygens. What makes these really interesting is that it can actually be both simultaneously in different localized regions of the glass. It's also worth noting that the bond strengths will determine the strengthening effect of these network formers, as well as the chemical durability of the glass. Aluminum oxide has a much stronger bond strength than zirconium oxide versus iron oxide versus calcium oxide. So these additions also contribute to those macroscopic properties.
And chemical durability, for those who don't know, is a material's ability to resist chemical, physical changes, decomposition, things like that when it's exposed to external agents. And this is really important, especially for glass, because if you think about it, you're constantly likely, if you keep clean, constantly spraying chemicals and water and things on these glass. And so if you have something that negatively interacts with that, you're damaging the glass. So you want to have a high chemical durability so that your glass isn't falling apart after a few years of water and chemicals hitting it.
Yeah, I feel like I've seen glasses where it looks like it's been etched away a little bit.
Yeah.
And like harsher chemicals can do that if it's a cheaper glass, or maybe it doesn't have that chemical durability.
Or maybe they're just using the wrong kind of glass cleaner.
Well, this is why glasses that are used for lab equipment are very different than what's used on windows, because it's a much harsher environment that they're dealing with. Now, this whole distinction between network former, network modifier, and intermediate is traditionally how it's been viewed, but it's considerably more complicated. And these days, there's more of a continuum rather than discrete understanding. This is due to coordination flexibility, composition dependence, processing effects, and even competing interactions between different intermediates. So it's a much more dynamic system than is being presented, but hopefully this is a helpful overview. Before we get into LionGlass specifically, it's just worth mentioning the compositions of some common ones like soda-lime glass, which is what a lot of black glass is made of, or what windows are largely made of. This is typically going to be made from silica, sodium carbonate, and calcium carbonate. The carbon is going to get burned off in the process, but you can see that in doing this, we're adding sodium and calcium to try to lower that melting point. And it's around 1500 C versus pure silica is about 2000 C. Borosilicate glass is very similar, except it adds boron oxide to change the thermal expansion coefficient. These have been silicate-based glasses, but the LionGlass from John Morrow's group does something different in an attempt to really bring down that melting temperature. It's a phosphate-based glass.
And people have been aware of phosphate glasses before, right? This isn't like a new invention.
Yeah, they're not necessarily brand new. They've been understood and known, but typically their chemical durability and their strength and other properties haven't really been up to par. Right now, there's a lot of research on them for nuclear waste containment, but not so much in terms of replacing things like windows. If you look in the literature, you can find plenty of articles about ZASP glasses, which are What?
Is zinc aluminosilicate glasses, which is technically the family that this falls under.
So in their paper that they put out in July, they present a composition of some glass that's from this larger LionGlass family of glasses that they're describing.
So let's go through the 3 categories for the composition of glass then. What are the network formers?
Right, so the main one that I mentioned is phosphorus pentaoxide. It's the dominant network former. They also have a little bit of silica in there too. And phosphorus pentaoxide is very interesting because it takes on a +5 charge state. So for its tetrahedra, it actually has a non-bridging double bonded oxygen and then 3 bridging oxygens. And then depending on the number of modifiers that are present, you can reduce the number of bridging oxygens that are there. These tend to be weaker bonds compared to silica, and so the melting point is definitely lower as a result of this.
And it is worth noting, when you say main, you really do mean main. It's 40 mole percent, and the silicon oxide is only 15.7 mole percent. So it takes up a much larger portion than anything else. So what about the modifiers?
Yeah, this tends to have very traditional ones in terms of sodium and calcium. There's also some magnesium oxide thrown in there. I'm not exactly sure. That's an intermediate that could play a number of different roles. But it's likely there to improve the processing window would be my guess. I think where it really gets interesting is in the intermediates. It has 2. First, it has alumina that's being added. This is probably being added to mostly strengthen the network and try to probably increase the melting temperature a little bit and improve the chemical durability and strength of the overall glass. Looking at the amount of modifiers that are present, it's potentially shifting alumina into a network former state. The other big one that's being added at 18 mole percent is zinc oxide. And zinc oxide is very interesting because it can form a tetrahedra, pentahedra, or octahedra simultaneously. So it can play a lot of different roles. But what's really interesting is there's a study they reference in the paper where under pressure, zinc can change its coordination environment, transitioning through basically depolymerization and then repolymerization as a function of the applied pressure. And what this flexibility does is it allows glass to accommodate mechanical stress or pressure that's applied to it through like a reversible structural reorganization rather than fracture. Basically, it's an energy absorption mechanism.
I was going to say that is huge for glass because obviously glass is famous for...
It's very brittle.
Yeah, it's being brittle and cracking. So being able to actually absorb some amount of pressure before that happens is a big deal.
Exactly. And, looking at through this composition, I'm by no means a glass expert, but especially when you look at it within the literature, a lot of the explanations and the additions to try to improve the performance of phosphate glasses, which were known for being rather poor, make a lot of sense.
Okay, so now we have an idea of the composition, and they added a lot of things into it, but the big target that they were going for is lowering the melting point and the forming temperatures. And this is a huge deal. LionGlass actually melts at about 1100 degrees Celsius, whereas sodium lime silicate melts at about 1500 degrees Celsius. So it's a big difference. And the reason this matters so much, excluding anything to do with human properties, is just the fact that you're saving a lot of energy, and in doing so, you're also cutting carbon emissions. I think it's very funny. They kind of focus on the carbon emissions side, but I was like, also, if you think about it, you're saving a lot of money because every time you don't use energy, that's a lower energy bill. And then also, your furnaces don't have to be as good. They don't have to get as hot. They don't get as much thermal stress on them. Like across the board, I don't know how expensive it is to get the components, but at least on the heating side, you do save some money.
Yeah, potentially a huge win if it can be scaled up. The other thing is they mentioned in their article the ability to source a number of the intermediates and the modifiers in non-carbonaceous forms. So rather than using sodium carbonate or calcium carbonate, they can actually get them bonded to a phosphate and add things together through there. I'm not sure what the cost difference is. It's always really hard to determine with these because economies of scale with the existing glass industry kind of obfuscate the true cost of things relative to one another. But that could also potentially lower carbon emissions through the precursors.
Yeah, so obviously that's so important because, normally when it gets heated up, they create this CO2, and then also you're saving in the energy, which is CO2. So it does appear to be more environmentally friendly.
But melting point's not everything in terms of glass. A lot of people are interested in the formability and the relaxation as it cools down. This is typically going to be looked at in terms of its glass transition temperature. It has a glass transition temperature of about 444 degrees C versus the 570 C for soda lime glass, so another reduction there. And it has this fragility index of about 36. Fragility is such a strange term for this.
Yeah,
it basically measures how sharply the viscosity increases as temperature drops towards your glass transition temperature. And it's about 36, which is similar. And basically what this means is that lime glass relaxes structurally at a similar rate as soda lime glass, but at a lower temperature.
Yeah, which is obviously good for people who want to work forming glass or things like that, because it means that they're still getting a similar behavior for glass forming, but at a much lower temperature.
What about hardness?
So lime glass does have a lower indentation hardness than typical glass, which means it probably will scratch easier and it may not be as hard, but...
Yeah, and a lot of that's due to those just weaker phosphate bonds.
But I guess it's sort of a question of use case. You know, if you're not worried about things scratching or hitting it, then it may be worth the savings in energy and also in emissions.
Yeah, but remember, we mentioned that it has that zinc oxide. It has a lot of it in there. And zinc has that great ability to change its polymerization, its coordination environment as like an energy dissipation mechanism. And this actually helps it because lime glass has like 10 times the crack resistance compared to soda lime glass. Even at 1 kilogram force load, they don't reach like 50% crack initiation. If you look in their paper, they have like their like indentations where they show like they're putting this pyramid indenter into it. And for the soda lime glass, you see cracks that are propagating off of it.
Yeah.
But for the lime glass, they don't see any. And in fact, they took their indenter to its maximum level and they weren't able to get a consistent crack formation.
So that's interesting. So it almost means that this glass, while it may get a little more banged up, it won't crack or break in the same way. So maybe you'll have a few more scratches and dents in your glass, but you won't have actual cracks ruining the entire glass. The next property is the coefficient of thermal expansion. And obviously, this is kind of an important one if you think about the fact that glass is often used in places that get heat, for example, your windows. So you need it to have at least similar, if not better, thermal expansion, because the last thing you want is your glass swelling up on you, because obviously it is meant to sit in these spots that hold the glass pane in. So if it expands, it's not great. And actually, the coefficient of thermal expansion for lime glass is lower than soda lime when you're below 270 degrees Celsius, which is fine because I don't think there's a lot of use cases for glass above 270 degrees Celsius, unless I guess maybe for oven glass. So I don't think it's a huge issue.
Okay, but elephant in the room for me is it transparent? You know, if this is going to replace Windows,
yeah,
then,
obviously that is the most important thing.
And it turns out that it is. It's effectively very similar in the visible light range to soda lime glass. There's some slight difference, but I don't think human perception could tell.
It's one of those things where if it's a negligible difference and you're getting other benefits, then there's no reason not to switch.
Yeah, and I mean, this is to say, like, even though it has phosphates, which can have like weird connectivity, it's sufficiently connected, probably because of the silica and the alumina and maybe the zinc, to reduce scattering and maintain that high transparency. The other thing that's really important is fining behavior.
What is fining?
Just during processing, you can get air bubbles and other sorts of gases that are stuck in it. And so fining is just the process of heating it up just enough so that the viscosity lowers so that bubbles can escape.
Okay.
And it has a lower fining temperature, meaning that you can do this process at a much lower temperature compared to soda lime glass as well.
Oh,
and it's really just because of the lower viscosity for the same temperature range.
Yeah, so in a way, there's also a little bit of energy savings in the production of it then too, not just the melting.
Yeah, it extends beyond just the melting.
Yeah, but in the fining as well. I mean, across the board, it obviously it's early. It really does seem like there are a lot of benefits. There are a few drawbacks and things to figure out. And you make a great point about the economy of scale. Like we have built the massive industry for years around one specific type of glass. And even recycling and other things like that are going to be a new challenge, and they're going to be different than how things are done. But it does seem like it could be a promising type of glass, at least for specific applications for sure.
Yeah, actually, from John Morrow himself, we had reached out. He had said beyond its practical use as a low-carbon alternative to traditional soda lime silicate glass, his hope was that lime glass could capture the public's imagination about what's possible within material science and engineering, especially within the field of glass. And in researching for this episode, I learned a lot more about what could be done with glass and that it's more than just silicates, and that there's a lot of really interesting chemistry and physics going on there. And if this became possible much later than the discovery of phosphate glasses, what other treasures are awaiting in the chemical world of glasses?
You know what a big thought I was having too is, and this is silly, but for people who want to do like glass forming as a hobby, theoretically, this would create a lower barrier of entry if the furnace and things don't need to go as hot and things like that, because it means that you could get gear that isn't as expensive.
Yeah, possibly.
Yeah.
I mean, another thing is
big
if
possibly,
all
obviously.
of a sudden your crack resistance is lower, there's a chance for lightweighting, potentially reducing the amount and the thickness that you need.
Yeah.
Well, this has just been a really exciting episode. I feel like we both learned a lot, and I hope, just as John Morrow said, that this inspires more people to consider glass and what's possible within it. If you've been listening to the last couple episodes, you may already be familiar with the American Ceramic Society's bulletin, but did you know that you can also write for the bulletin? Each bulletin issue offers exclusive content written by industry experts, thought leaders, an in-depth discussion of market trends and technical insights, and extensive coverage of the latest innovations in the ceramic and glass material science space. In writing for Acers, you'll work directly with their editor, who will help your research and expertise shine, putting your best foot forward. And thank you for the American Ceramic Society for sponsoring this episode. If you are an expert in the glass or ceramic space, consider writing an article for their bulletin.
The Materialism podcast is also sponsored by Materials Today. Visit materialstoday.com to stay up to date on the latest happenings in the material science field and read some of the fantastic articles that they have published. You can also head over to elsevier.com to find out more about their journals, books, conferences, and related programs.
As always, thank you for listening to this episode of the Materialism Podcast. If you have questions or feedback, please send us emails at materialism.podcast@gmail.com. Make sure you subscribe to the show on iTunes, Spotify, YouTube, or wherever you find your podcasts. And if you like the show and you want to help us reach more people, consider leaving a review, telling us what you think, how we can improve, and what material you'd like to hear about next. Finally, you can check out our Instagram page at materialism.podcast and see lots of cool art, connect with us, message us, and help us shape the future of the Materialism Podcast.
We'd like to give a shout out to Alphabot and Kolobyte for making music for this podcast. They make a ton of cool synthwave stuff. You can find them on Spotify and YouTube. Thanks for listening.
Catch you next time.
The inventors of fire, electricity, magnetism, iron, lead, glass, silk, cotton, the makers of tools, the captors of lightning, the architect, the engineer, the musician, are all beneficiaries of the materials of this world, and are bound only by their imaginations in manipulating those materials.